Hey, ooh. Hey guys, I'm at a meet tomorrow. I'd like to briefly talk about some topics that you're going to practice tomorrow in class, and hopefully that'll become solidified in your mind after watching the screencast and then practicing them tomorrow. Okay, so we have first off, right, we're not going to practice these ones tomorrow. These are a little dense, and I want to sort of be there when we really work through them. So we're going to look at these early next week. So we're going a little bit out of order here, but that's fine. We're talking about inverse trig integrals or inverse trig derivatives. And these are formulas that you probably saw last year, but maybe weren't assessed on. But these are things that we're going to have to know. And I'm going to start putting these on assessments so that we know them. Obviously, we'll practice them first. Okay, so I just want to draw attention to that these things sort of come in pairs as you start to memorize them, right? Then we think about the graphs of trig functions that are sort of very similar, right? Sine and cosine are very similar. Tangent and cotangent are very similar in terms of graph, and secant and cosecant are very similar in terms of graph, right? And if we look at these, right, the sine and cosine are just, there's an extra negative sign in there. And tan and cotangent, there's an extra negative sign in there. And secant and cosecant, there's an extra negative sign in there. So all we really have to do is memorize the patterns on the left and then sort of know that the patterns on the right are the negative versions. Okay, but we don't have to really worry about that today. What we're going to talk today about is U substitution, or undoing the chain rule. And if we think about the chain rule, right, the chain rule where I have a function of a function, right, we sort of see that function's derivative come out when we take a derivative. So let's see if we can identify that the chain rule has been applied here. We arrive at an accident, right, and we see that a chain rule has been applied, okay? So if I look at this thing and I say I see two functions here. I see this function and I see this function, red and blue. And I think you guys would agree that if I look at the derivative of the red function, right, this thing is that blue function. Okay, so if we see a function and its derivative, it's sort of an indication that the chain rule has happened. Okay, and I could potentially FOIL this thing out on the left. I could FOIL out x squared plus 3 to the fourth, but that sounds very, very messy, and I don't necessarily want to do that. So what we're going to do is we're going to convert to a different land. So our sort of step one is that we identify that there's a function and its derivative, right? So I'll keep a running list of steps over here. Well, maybe over here. So identify a function and its derivative inside an integral, right? And it's inside an integral. Okay. And then we're going to say that original function, we're going to actually label that u. So our first step is our second step, is we're going to convert to, and I'm going to say uland. And what that means is we're going to say that u is going to equal x squared plus 3. And if u equals x squared plus 3, I could take the derivative of both sides of this with respect to x. So I'll get du dx on one side, and I'll get 2x on the other. And if we think about this, right, I know this is not really a fraction, right? But if we think about this as a differential, I'm going to multiply by dx, and I could say something like this. So we're going to keep track of these two things. I'm going to box them in red and blue so that we can sort of, rewrite ourselves in uland. So convert to uland once we've identified these functions. So I should say a function, and then we'll put u, and we'll say du over here, okay? So a function that's derivative, u and du, and convert to uland. Okay, and so what I mean by that is let's rewrite this integral with respect to u. So I have here the integral of x squared plus 3 to the fourth. We'll zoom out a little so we can actually rewrite it. Okay. Might be a little cramped for space here. Okay, and this thing equals, well, x squared plus 3, that's just u. So this is going to be equal to u to the fourth. And this 2x, right, that's this red guy. And then this 2x dx, well, that's what we said du was. So I can rewrite this whole thing as du. okay? You should pause the video if this is confusing to you and rationalize that I can just rewrite this whole expression in terms of u, right? This thing here is u to the fourth, x squared plus 3 is u to the is u. Right, x squared plus 3 to the fourth is u to the fourth. And 2x dx, that is just du. Okay, I'm going to now take the integral. So step 3 would be take the integral in u land. Okay, now we didn't want to take that integral initially, right? Because we would have had to FOIL x squared plus 3 to the fourth. And that looks very messy. But in u land, the integral of u to the fourth du, well, we know that, right? That's just 1/5 u to the fifth plus c. That's very easy, right? Very easy. So we should think this should be easy. Should be easy. If we picked u correctly, that integral should be very simple. Okay, so we take the integral with respect to u. Okay, and then our last step is going to be convert back to x land. Convert back to x land. So going back to x land, right? This thing, what was u? U was x squared plus 3. So this thing would just have 1/5 x plus 3 to the fifth plus c as its integral. Okay, now let's just check ourselves, right? We don't always have to do this, but let's check ourselves. So check, let's take this thing's derivative. Okay, let's take this thing's derivative, and we'll hopefully see that we get the right answer. Okay, so if I take this derivative with respect to x, right, I have this 1/5 floating outside, I bring down a 5, I have this thing to the fourth, and then of course I need to take the derivative of this inner function, which is just 2x. And would you look at that? That's exactly what we started with, okay? So the goal is of sort of undoing the chain rule, right, is to pick a u intelligently so I could take integrals that would previously be quite difficult. Okay, so let's try an example, and I would like you to pause me and then try it after I sort of write this down. So let's think about let's do 3x squared plus 4 times e to the x cubed plus 4x dx. And I obviously forgot an integral sign out here. Okay, so pause me, try to set up a u substitution, and then unpause me. Okay, I hope that worked for you. Okay. Do we identify a function and its derivative in here? And the answer is of course, right? Here's my function, x cubed plus 4x. And here's its derivative, 3x squared plus 4. So I might want to rewrite this. As e to the x cubed plus 4x. We'll see why in a second. 3x squared plus 4 dx. Well, we identified the sort of the red function and the blue function. Right, the function and its derivative. Okay. Function and its derivative. Let's set u equal to the function. Let's take its derivative. Oh, look, there it is. Let's multiply by dx. Okay, now I can go to u land. So this original function is really what? This original function, e to the x cubed plus 4x. Well, that just sounds like e to the u. And then this whole blue expression over here, 3x squared plus 4 dx, that's just du. Right? That's just du. Okay? So, this is kind of a fun one, right? The integral of e to the u du is just e to the u plus c. Just e to the u plus c. And so that e to the u, right, that going back to x land is just e to the x cubed plus 4x plus c. And if you think about this, right, this thing's derivative is certainly that initial integrand that we had, right? So we're done here. We're done. X cubed plus 4x, e raised to that power. Okay? So this is a very, very powerful tool. Picking u can be tricky. Okay? It can be quite tricky. So we're gonna do one more example on this video, and then we're gonna be done. Okay, this one you might have some leeway with. Okay, you might have some leeway with. There are two choices, and I want you to try to do one here and then maybe one in class. Okay, so fortunately or unfortunately for you, I don't know which one. Trig functions are often each other's derivatives, right? So if we think about the integral of sine x cosine x dx, that thing looks very, very scary, right? What on earth has the derivative of that? Well, we got to do a little work here, okay? So, integral of sine x cos x. You got to do a little bit of work here because it's not immediately obvious what to pick. But if we think about it, does a function and its derivative live here? Why, yes, because sine's derivative is cosine, right? So pause me and try to make that u sub and see if you can get somewhere that works. Okay, hopefully you got somewhere that works, right? You should have said something like, oh, if my function would be sine x, and then my du dx would be cosine x, and therefore my du is cosine x dx. So coming back up here, the integral of sine x cos x dx could be rewritten as the integral of u du, which of course is just 1/2 u squared plus c. Well, u is just sine x, 1/2 sine squared x plus c. And if you were to take this function's derivative, you guys would get sine x cos x. So your one homework problem tonight that I'd like you to try and I'd like you to discuss tomorrow 6th period with each other is what happens if we try to do the same problem and I picked u as cosine x. Okay, I want you to pick u as cosine x, and I want you to try to handle your negative sign, and then think about, do I get the same answer up here, or do I get something different? And then if you're confused in class tomorrow or at home right now, why don't you graph them on Desmos, and then maybe you'll be able to say something smart. So we're going to practice u sub tomorrow. That'll sort of be your work over the weekend, I think. Maybe also reviewing some trig derivatives. I haven't quite seen what exactly I want. We might go back to derivatives to review that kind of material. I hope this was helpful, and I'll be available if you have questions on Friday.